In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about heavy ion fusion cross sections of weakly bound beryllium and aluminium, zinc, and tightly bound oxygen and zinc target using Colombo and proximity potential. It was written by Santosh and Jose, School of Pure and Applied Physics, Kannur Universities in India. The total fusion cross-sections for the fusion of weakly bound beryllium and aluminum-27 and zinc-64 targets at near and above the barrier have been calculated using one-dimensional barrier penetration model taking a scattering potential at as the sum of Colombo and proximity potential, and the calculated values are compared with experimental data for the purpose of comparison of the fusion of weakly bound projectiles and strongly bound projectiles. The total fusion cross sections for the reaction of tightly bound nucleus oxygen 61 zinc 64 have also been computed using a similar procedure. The calculated values of total fusion cross sections in all cases are compared with coupled channel calculations using the code CC fuel, and the computed cross sections using Colombo and proximity potential explain the fusion reactions well in both cases of weakly bound and strongly bound projectiles. Reduced reaction cross sections for the system beryllium positive and beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64 and oxygen 16 plus zinc 64 have also been described. Now I want to go through the introduction. As the synthesis of superheavy elements is a hot topic and very interesting problem nowadays. Many investigations, both experimental and theoretical, on heavy ion fusion reactions at above and below the Colombo barrier have been an area of extensive studies in nuclear physics. Considerably high beam intensity of stable weakly bound nuclei compared to the radioactive beams make the study of the fusion of weakly bound nuclei and the influence of the breakup process in the fusion reactions an important subject of detailed and in-depth investigation in heavy ion fusion reactions in the fusion process, and more specifically in the fusion of weakly bound nuclei. Several reaction mechanisms followed by the breakup of the projectile have to be considered both experimentally and theoretically. Incomplete fusion reaction ICF, when part of the projectile is captured by the target, and complete fusion CF with the capture of all of the projectile constituent by the target. Target fusion, or TF, is understood as the sum of these two processes, CF as a complete fusion and ICF as a incomplete fusion reaction. In the analysis of heavy ion fusion reactions, an internuclear interaction consisting of repulsive Colombo and centrifugal potential and attractive nuclear potential plays a major role, where the potential is a function of the distance between center of mass of the colliding nuclei. At a distance referred to as a Colombo barrier, the total potential attains a maximum value where the repulsive and attractive forces balance each other and energy or relative motion must overcome this barrier in order to nuclei to the capture and fuse. In the present work, the fusion excitation functions for the fusion of weakly bound beryllium 9 and aluminum 27 and zinc 64 targets have been calculated using one-dimensional barrier penetration model, taking a scattering potential as the sum of Columbus and proximity potential, and the calculated values are compared with the experimental data. For the purpose of comparison of the fusion of weakly bound projectiles and the strongly bound projectiles, the total fusion cross sections are the For the reaction of tightly bound nucleus, oxygen 16 and zinc 64 have also been computed using similar procedures, and the results are compared with the experimental data. The calculated values of total fusion cross sections in all cases was compared with Cook's channel calculations using the code CC fuel reduced reaction cross sections for the system beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64 have been described by using the usual reduction procedure of dividing the cross sections by p r0 to the power of 2, where r0 is a barrier radius and the division of energy of Colombo barrier. Now I want to go through the theory 2.1, the first sections of the potential theory, describing a unique nuclear potential for exploring different nuclear reaction mechanisms which are exclusively governed by the nucleus. Nucleus potential is an extensive challenge for the last several years in nuclear physics, explaining the nuclear potential as a product of the geometrical factor which is proportional to radius of colliding nuclei, and any universal function is commonly accepted as it is incorporating the role of the different colliding nuclei and in the geometrical factor. In this effort, a simple formula for the nucleus interaction energy as a function of separation between the surfaces of the approaching nuclei has been given by the proximity potential of Bloch and his colleagues in the reference 70. The formula is free of adjustable parameters and make use of the measured values of the nuclear surface tension and surface diffuseness. The interaction barrier for two colliding nucleus is given as the V is equal to Z plus N to e to the power of 2 divided by R plus V PZ plus h to the power of 2 L multiplied by L plus 1 divided by 2 micro R to the power of 2, where Z1 and Z2 are the atomic numbers of projectile and target. R is the distance between the centers of the projectile and target. Z is the distance between the near surfaces of the projectile and target. L is the angular momentum. Micro is the reduced mass of the target and projectile. And VPZ is the proximity potential, given as VPZ is equal to 4b gamma b multiplied by C1 C2 divided by C1 plus C2 phi Z divided by B with the nuclear surface tension coefficients. Gamma is equal to 0.9517 multiplied by 1 minus 1.7826 multiplied by n minus Z to the power of 2 divided by R to the power of 2. Phi, the universal proximity potential, is given as phi zeta is equal to minus 4.41 exponential minus theta divided by 0.7176 for zeta is greater or equal to 1.9475. The phi zeta is equal to minus 1.7817 plus 0.9270 zeta plus 0.01696 zeta to the power of 2 minus 0.05148 zeta to the power of 3, for zeta is between the 0 and 1.9475. Phi zeta is equal to minus 1.7817 plus z 0.9270 zeta plus 0.0143 zeta to the power of 2 minus 0.09 zeta to the power of 3, with the zeta is equal to z divided by b, where the wide diffuseness of nuclear surfaces b is almost equal to 1 and sigma central radius ci related to Schur radius ri, as ci is equal to ri minus b to the power of 2 divided by ri. For ri, we use the semi-empirical formula in terms of mass numbers r I as Ri is equal to 1.228 I to the power of 1 per 3 minus 0.76 plus 0.8 I to the power of minus 1 divided by 3. The choice of the potential and its form to be adopted is one of the most challenging aspects when one wants to compare the experimental fusion data with theory. Among such potentials, the proximity potential is well known for its simplicity and numerous applications in different fields. It is based on the proximity force theorem, according to which the nuclear part of the interaction potential is a product of the geometrical factor depending on the mean curvature of the interaction surface and universal function depending on the separation distance, and is independent of the masses of the colliding nuclei. The next chapter is the fusion cross-section. For the last 4 decades, the barrier penetration model developed by C. Wang has been widely used to describe the fusion reactions at the energies not too much above the barrier and at higher energies, which obviously explain the experimental result properly. Following Thomas and Heizuka and his colleagues Ego, the Rasmussen and Sugawara, Wang approximated the various barriers for different partial waves by inverted harmonic oscillator potential of the height EL and frequency omega L for energy E using the probability for the absorption of LT partial wave given by the Hill-Wheeler formula. Wang arrived at the total cross-section for the fusion of the two nuclei for quantum mechanics quantum mechanical penetration of simple one-dimensional potential barrier as sigma is equal to p divided by chi to the power of 2 sigma. Lower boundary is L, 2L plus 1 divided by 1 plus exponential 2p El minus E divided by h omega L, where chi is equal to square root of 2 micro E divided by h to the power of 2. Here h omega L is the curvature of the inverted parabola. Using some parameterizations in the region n is equal to 0 and replacing the sum in equation 8 by an integral 1 gave the reaction cross sections as sigma is equal to r0 to the power of 2 h omega 0 divided by 2e ln 1 plus exponential 2pe minus e0 divided by h omega 0 for relatively large values of e. The above result reduces the well-known formula sigma is equal to p r0 to the power of 2 multiplied by 1 minus e0 divided by e. The reduced reaction cross sections, a common procedure of eliminating the geometrical factors concerning different systems by reducing the cross sections at the center of mass energy, has extensively been used in recent years for the comparison of the excitation functions of different reaction mechanisms induced by different projectiles on the same target nucleus. The normal procedure consists of the division of the cross sections by r0 to the power of 2, where r0 is a barrier radius and the division of the energy by Colombo barrier is 0. The result and discussions. For N is equal to 0, the interaction barriers for the fusion of the systems beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64 with Colombo and proximity potential have been plotted in figure 1 against the distance between the centers of the projectile and the target. The values of the barrier height is 0 and the barrier radius are 0 for the reactions are noted. It is to be noted that the system oxygen 16 plus Zinc 64 has maximum barrier height E0 and the barrier radius R0 in the case of the reactions of weakly bound projectile beryllium 9 on aluminum 27 and zinc 64. As the mass of the target increases, the barrier height E0 increases and the barrier radius R0 shifts toward large value above the Coulomb barrier. The total fusion cross sections for all reactions have been calculated by using the values of barrier height EAB and the barrier radius RAB taken from the respective figures and using equation 8 in the reaction of beryllium 9 plus aluminum 17, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64 above the barrier. The total fusion cross section is computed using one is formula with Colombo and the proximity potential given by the equation 8, and the corresponding experimental values are shown in the table 1, 2, 3, and in the figure 2, 3, 4. In the figure 2, 3, 4, and the dot lines represents calculations using no channel couplings, and the solid lines represents the vibrational couplings in the target while using the code CCF, whereas paired transfer channels is not included. A radius parameter of RS is equal to 1.2 fm, which the formation parameters Betsoy lambda n is equal to Betsoy lambda c is used all in all calculations. The depth parameter V0 and the surface diffuseness parameter I0 for the nuclear potential of the Wood-Saxon form in the coupled channel calculations using CC fuel have been calculated with R0 fixed at 1.20. In figure 2, in the case of the reaction of a weakly bound projectile beryllium 9 and aluminum 27, the target above the barrier and the total fusion cross sections down triangles computed using equation 8 fit reasonably with the experimental data circles while using the scattering potential as Colombo and proximity potential. The depth parameter V0 and the surface diffuseness parameter I0 for the nuclear potential and fuel calculations have been taken as 40.40 megaelectron and 0.60 fm respectively. In the CC fuel calculations couped of the beryllium 9 and plus aluminum 27 reaction, the single phonon excitation with Betsoy 2n is equal to 0.448 and excitation energy 1.014 megaelectron of aluminum 27 is used, where the weakly bond projectile beryllium 9 is kept inert. In the case of the CC full calculations, which no couplings uncoupled, almost no difference between the two calculations can be observed in comparison with coupled calculations are expected at these energies above the Colombo barrier. In the case of reaction of weakly bound beryllium 9 and strongly bound oxygen 60 projectiles on Z N or zinc 64 target above the barrier, the total fusion cross sections down triangles computed using equation 8 show good fit which the experimental data circles its irrespective of the fact that barium non-projectile is weakly bound and oxygen 16 is strongly bound as shown in figures 3 and 4. The dot lines and the solid lines in the figures 3 and 4 show the CC fuel calculations without and with coupling respectively. In all CC4 calculations, the single phonon excitation in zinc 64 with Betsoy is equal to 0.236, and the first two excited state of the target with the excitation energies 1.799 megaelectron volt and 0.991 megaelectron volt have been used, where the projectiles are kept inert. The V0 O0 parameters for the reactions beryllium 9 plus zinc 64 and oxygen 16 plus zinc 64, the CC full calculations have been taken as 46.23 megaelectron volts, 0.62 fm, and 54.94 95 megaelectron volt and 0.64 fm respectively. In the case of the weight ammeter couplings, almost no difference between the two calculations can be observed, just as it is expected above the Colombo barrier. The comparatively good agreement between all calculations with experimental data, at least within the experimental uncertainties, it can be proved that the total fusion cross-section calculations for the system are not affected by the breakup process at energies above the barrier while using Colombo and proximity potential. If the computed fusion cross-sections for the system oxygen 16 plus zinc 64 which is strongly bound projectile is directly compared with the system beryllium 9 plus zinc 64 which loosely bound projectile. Contribution of the geometrical factors such as the size of the projectile influences as the result. For eliminating the effect, we have renormalized the cross sections with respect to the geometrical value and incident energy with respect to the barrier height for the system beryllium 9 plus zinc 64 and oxygen 60 plus zinc 64. Figure 5 represents the corresponding reduced reaction cross sections by the usual reduction procedure of the dividing the cross sections by PR0 to the power of 2 and the energy by E0 so as to compare the two systems on the same figure as the cross sections for the two systems that are rather similar as shown in figure 5. It can be concluded that the static effects arising from the weakly bound nucleus don't affect the fusion cross-sections above the barrier, and moreover the dynamic channel coupling also are not relevant above the barrier. Now I want to go through the conclusion. Interaction barriers for the fusion of the systems beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64, beryllium 9 plus zinc 64 have been plotted against the distance between the centers of the projectile and target. It is noted that the barrier height is 0 and the barrier radius R0 are greater for systems oxygen 16 plus zinc 64. The total reaction cross sections of the systems beryllium 9 plus aluminum 27 and beryllium 9 plus zinc 64 and oxygen 16 plus zinc 64 have also been computed, and the results are compared with experimental data and Cooped channel calculations using cold CC fuel while using the scattering potential as the sum of the Colombo and proximity potentials above the barrier. The simple one-dimensional barrier penetration model developed by C.V. Wong explains the fusion reactions of heavy ions reasonably well, irrespective of the nature of the projectiles, either a weakly bound or strongly bound. The reduced cross sections compared the different fusion reaction mechanisms induced by different projectile and targets in the same figure as the reduced reaction cross sections for the systems beryllium 9 plus zinc 64 and oxygen 16 plus Z60, Zn or zinc 64 are rather similar. It can be concluded that the static effects arising from the weakly bound nucleus don't affect the fusion cross sections above the barrier, and moreover, the dynamic channel coupling also are not relevant above the barrier. So thank you so much for watching my tutorial video on today. Also, I want to have a review on figures. Figure 1 illustrates color online scattering potential for the reactions of beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64, consisting of repulsive Colombo and centrifugal potentials and attractive nuclear proximity potential for L is equal to 0. You can see the x-axis we have a RFM, y-axis we have a volt, mega electron volt for dashed blue lines is beryllium 9 plus aluminum 27. Red dashed line is beryllium 9 plus zinc 64, and green line is oxygen 16 plus zinc 64. Figure 2 illustrates the color line computed fusion cross sections for beryllium plus aluminum 27 reaction using Wong's formula and their comparison with the experimental data and CC food. You can see that ECM mega electron volt in x-axis and E sigma MB in the y-axis. Figure 3 shows color line and computed fusion cross sections for beryllium 9 plus zinc 64 reaction using Wong's formula and their comparison with the experimental data and CC food. Figure 4 illustrates color line computed fusion cross sections for oxygen 60 plus zinc 64 reaction using Wong's formula and their comparison with the experimental data and CC food. Figure 5 illustrates color reduced reaction cross sections for the systems beryllium 9 plus aluminum 27, beryllium 9 plus zinc 64, and oxygen 16 plus zinc 64. Table 1 computed fusion cross sections for the system beryllium 9 plus aluminum 27. The comparison with experimental data, we Yes, see, we have a mega electron volt here in the left side, experimental data and the theory based on the equation 8, and experimental data based on the reference 13. It's the fusion cross sections here. Table 2 illustrates and describes the computed fusion cross-sections for the system beryllium-9 plus zinc-64 in comparison with the experimental data. Table 3 illustrates computed fusion cross-sections for the system oxygen-16 plus zinc-64 and in comparison with the experimental data. So thank you so much for watching my tutorial video until the end. Today is the 28th of June 2026. Time is 7 in the morning. And if there is any simulation for this literature for fusion cross sections for beryllium and also oxygen, zinc, and other elements, you can find it from my github.com/masterscript, github.com/kashi script, and slash also sephora script.